Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we did talk about a circuit with a pure resistance. We said a circuit that has only resistance. And of course, we were connecting a resistor, let's say with an alternating circuit, or you can say AC circuit. And of course, we did also connect a voltmeter and ammeter just to say, like, how would they change, let's say, with the alternating current. And of course, we noticed that when the voltmeter readings were going higher, the current with it were going higher as well. So in another word, when the voltmeter were reading maximum voltage, the ammeter were reading maximum as well. To put it in another way, or you can say to explain it in a different way, we were saying that the phase difference between the voltage and the current were zero. And of course, after that, we talked about the resistance that we've also found, which is obviously was, let's say, we did say that basically in another way to explain that, we said the opposition that, let's say, a resistor shows to the current that is passing through that one. Or you could say in another way, we've also said that the ratio between the maximum voltage across that resistor with, of course, in that pure resistance, let's say to the maximum current that were flowing through the resistor in a circuit, of course. And then after that, we ended up right at this point here. We were of course, now we're going to talk about a pure self-inductance here. So we're talking about an inductance, and of course we do, what is the difference between an inductance and a resistor? By the way, every inductant would have a resistor, let's say a resistance to it, but here when we say a pure inductance, that means an inductor with no resistance at all. Okay. So now that is what we're going to talk about. So of course, a pure self-inductance circuit, it is a circuit that consists of only an inductor with negligible resistance, or you can say the resistance for that one is going to be zero. And what exactly do we have? We have this one, let's say. So basically try to learn the difference between an inductor and a resistor as well, or their symbol at least. Let's say we're connecting this inductor with an alternating current, and of course you can say there is a switch as well. In order to, we need an ammeter to measure the current that is through the circuit, let's say, or passing through this one, and of course a voltmeter to measure the voltage across this inductor here. Okay, that is basically the symbol of an inductor. You can say L, and of course we do have, this is the symbol for a resistor as well. Okay, so this is basically what we have studied the other session, and of course we were connecting this one to an alternating current, and of course with an ammeter, and of course there were a voltmeter too. And we said here both the voltage, or let's say the voltmeter and the meter were, let's say, reading or the indicating to maximum voltage, maximum current here together, yeah, so simultaneously. While this one is increasing too. When this one started to decrease, this one decreased with that as well. So based on that, we said that the phase angle difference between the current and the voltage for a circuit that has only a pure resistance, let's say, it was zero here. And of course, we found the resistance of the circuit as well and all that, yeah? But that is the main focus for today. So we're going to talk about this one here. So we have a circuit with a pure inductance only. That means there is only an inductor with a negligible resistance right here. So what happens exactly when we close the switch? We will see that this voltmeter indicator is going to read, or let's say, show maximum voltage, while this one is still reading zero. Okay, and then we will notice that this one is starting to decrease while this one is going to increase until it reaches maximum. When this is maximum, this one is reading zero. So what do we get from this? So we can tell that when this is maximum, this is zero. When this is maximum, this becomes zero. So based on this, of course, we can draw a sinusoidal wave for this. We can say if we have, let's say, a voltage, let's say, a line for sinusoidal for, let's say, for the voltage here, we can say this is maximum, and of course we can go with this. Let's make it more precise. So let's see if I can, yes, I think it is not bad. And something like this. This has to be the same thing. Let me redraw this one more time here, this part. Okay, so this is, let's say, the voltage. You can say that is basically the maximum voltage for the inductor. That is on the inductor. And then on the other hand, we have, let's say we have the current through this. While this is maximum, you can see here that the current is showing zero here. And of course, this is what happens. When the current is reaching maximum, you can see that this voltmeter is zero. And then, of course, it is going to decrease one more time. Okay, and one more time, you can see that the current is zero while the voltage is maximum. And then here again, when the current is maximum, okay, the voltage is zero. and of course is going to continue like this, like further more and more. So this is basically for the voltage, and this is for the maximum current for, or you can say on the inductor right here. This is basically the graph for there. And what would be the angle, or based on this, what can we say about the angle between the two here? And of course, regarding the angle, we can say that the angle between the two, let's say this is the maximum voltage on the inductor, and this is of course maximum current on the inductor. The angle between the two, we can say, is basically positive pi over 2. That is if you go by radian, of course, and then we also can say 90 degrees if we go by the degrees as well. Let's say this is the radian between the two. So once again, when we have a circuit that is connected to a pure self-inductance, remember this. If the circuit is connected, the voltmeter reads maximum voltage while the ammeter is reading 0. And then after that, the voltmeter, let's say, decreased to 0 while the current increased to maximum here. And then this is how it continues, let's say. So based on that, we can say the phase angle difference between the two is 90 degrees. But what exactly? Because the voltage starts to increase until it reaches maximum. So we'll say, remember this, we'll say the voltage leads the current by 90 degrees here. Or we can say another way, we can say the current lags or comes after, or let's say it is running behind by 90 degrees, or you can say pi over 2. So remember this. We're going to take a look at a few tips, and of course we'll come back to this to continue for the resistance of this, because this self-inductance, of course, it is a resistance, or this inductor provides a resistance, and we're going to talk about how this resistance can be found here. So the first one, at an instant when the voltmeter is reading maximum, the ammeter reads 0, and then when the ammeter reads maximum, the voltmeter becomes 0, and vice versa, let's say. So the reading of the ammeter is maximum, so we've mentioned that. The potential difference leads, so based on this, okay, we can say the potential difference leads the current by a phase of 90 degrees or pi over 2 radian. If not, we can say, instead of saying the voltage leads by 90, we can say the current lags behind the potential difference by a phase of 90 degrees or pi over 2. But watch this, we cannot say the voltage leads by 90 and the current lags by 90, because that is going to be incorrect, because what you're saying is basically 180 degrees between the two, which is incorrect. And of course, a pure self-inductance, you can say, depends on the frequency of the voltage. One thing that we've mentioned for the resistor or pure resistance circuit, let's say, we said that it doesn't depend on the frequency of the source, of the frequency of the alternating current, let's say, but this one, of course, it does. And of course, we're going to see that it is directly proportional. In another word, you can say the bigger the frequency, the more the resistance there will be. Okay, so take a look at this one. These are the circuits. So we've mentioned this one as well. So pure inductor under the AC source, the potential difference of the current basically across the pure self and AC circuit. So part A, that is going to be the current through the inductor, and of course the voltage over the across the inductor in terms of time. And for the second part, you see that that the voltage leads the current by 90 degrees or pi over 2. So how can we write because the value of this, or you can see these are alternating currents, so these values are continuously changing, yeah? So how can we write their instantaneous values here? Now we can add up this one to what we have said, because these values are changing, so of course these have instantaneous values. So how are we going to add up their instantaneous? For the voltage, we can say V instantaneous, or we can just say V sub L, that is the voltage across the inductance, that is instantaneous as well. We can say V maximum, okay, and then let's read maximum a little bit closer. So V maximum sine omega t, all right, but remember, because we said it is leading by 90, so of course we will say omega t plus pi over 2 radians, yes? Remember this is basically that is the voltage or instantaneous voltage. What about for the current? Yeah, for the current we can say I instantaneous for the that passes, let's say, through the inductor. We can say I maximum, okay, that is sine just omega t, okay? Remember this, that is sine omega t. Now based on this, we can see that the voltage is leading by pi over 2 or just 90 degrees. There is another way to write this one, by the way. If we don't want to, or if this one is not written this way, there is another way. If you remember one of the notes, we said is either the voltage that is leading by 90 or it is the current that lags by 90 degrees. So how can we translate that into an equation, let's say? So of course, now instead of this, let's use different colors here. Okay, now instead of this one, we can say, we'll rewrite the same form, but in a different way. We'll say V over, all right, instantaneous voltage, we'll say V maximum sine omega t. But remember, I did not write the plus pi over 2, yeah? But if that is the case, then I'll have to take away pi over 2 from the current, because this time the current is going to lag by 90. So I'll say I max, okay, sine omega t, but this time negative or minus pi over 2 radians. So you see the difference or what I wrote here? So we'll either say the voltage leads by pi over 2 or the current lags by. If I don't add anything here, so I'll have to say the current lags by pi over 2, and that is basically 90 degrees. Okay, and these are basically the equations for what? These are the equations for the instantaneous current, the current at every second or at every instant. This is how it can be found. So based on this, we can say for this part, the voltage leads by 90 degrees, or here we can say the current lags by 90 degrees. So whichever you go with, these are totally fine, but it's very important to notice like which one of these equations are given in the question so that you know what is next. For example, let's just say if you're given an instantaneous equation, let's say this one in one of the equations, and they ask you for the instantaneous current, then of course you just write omega t for the sine, yeah? But if you're given this one here for a pure self-inductance in an equation, and they ask you for the instantaneous current equation, then of course you'll have to say negative or minus pi over 2. That is the point where you have to be careful with. The next thing that we have is inductive impedance, yeah? We do know that this inductor, of course, it provides some resistance, yeah? So what do we call this resistance? How do we define that? And then how do we calculate that, or how do we find that? So of course, for inductive capacitance, by the way, it is a type of resistance, and of course we'll use the word or X sub L here. That is basically the inductive, you can say, impedance or the resistance that is provided by the inductance here. We can say it is the ratio to the maximum potential difference across a pure self-inductance, we can say, to the maximum current through it, of course, in an AC current. And because it is a resistance, so it is measured in ohms. Another way to say that, we can say it is the opposition that an inductor provides to the current, of course, or to the alternating current that passes through it, you can say, which is, of course, depends on the frequency F, and of course, depends on the frequency of the alternating current, AC current, and also the value of the inductor itself as well. Okay, so what do we mean exactly by this? Okay, now take a look at what we have. So perhaps I can add this one to what we wrote there over there. Okay, so we can say or you can say inductive impedance. Remember this, that is a type of resistance equals to what? We said it is a ratio of maximum voltage to the maximum current as well. So this is one way to find, but hey, listen up. All right, watch this, if maximum or these values are not in maximum, we can use other values to find this one as well. Other values like what? We can use V effective with effective current as well, or you can say V root main square with root main square current as well. If not this, we can use the instantaneous values for this, that is V sub L, you can say, and of course we will use I sub L as well. So whichever these values that you're given, you can always use them to find the inductive impedance here. But one thing you need to know, it is always have to be the same thing. If it is maximum, you have to use maximum. If it is effective and effective, and of course this is instantaneous and instantaneous as well. Remember this, we cannot use V maximum with, let's say, I effective. No, these are not the same, so you cannot use this one. It has to be the same thing. So what do we do if we have one of them is maximum, let's say maximum voltage is given, or effective current is given? So of course we've learned a way to convert this effective either to maximum, so we will find I maximum, so that we can divide V maximum by current maximum, or you can convert or find V effective with I effective, then you can find the inductive impedance over there. So that is one way to do that. Of course, where do we get this one from, by the way? We get this one from Ohm's law because we said it is a resistance, yeah? If you remember, for pure resistance, we were saying R equals to V maximum over I maximum, yeah? Or let's say V effective over I effective, or let's say V over across the resistance over R that is passing through the resistance as well, yeah? But because it is a resistance, so we'll use the same equation for that. But there is one more thing, yeah? So what is this one is, by the way, measured in? This is, since it is a resistance, so it is measured in ohm. What about the voltage? That is basically measured in volt, and the other one is measured in ampere. But if you know that, we said that the self-impedance depends on the frequency, which means that there is another way to find the inductive impedance. So how do we do that? Well, say inductive impedance also equals to what? Equals to omega times what? Times the what was the other thing here? So times the value for the inductor as well. But you do know that if omegas are not given, we can say 2 pi times the frequency multiplied by the value of the inductor as well. Okay, so remember this. This is another way to find the inductive impedance here. So as you can tell here, this inductive impedance here, it is directly proportional. Inductive impedance is directly proportional to the frequency, and also it is directly proportional to the value for the inductor as well, which is basically measured in Henry. Okay, now, so as you can tell here, we have two ways to finding this. It is either by using omega L, and of course, or we can use Ohm's law to determine to find this value. And of course, we've mentioned that there. That is basically this is measured in. Let me go back to this one here. Okay, remember that if we're going to use this one, this is measured in ohms. Okay, this is measured in ohms. Not this. Okay, so this is measured in ohms. This is hertz, and of course, we can say this is measured in Henry as well. So of course, now you can manipulate this one in so many different ways here, for example, yeah? And we can say, for example, this is ohms, this is hertz, as you can see, this is Henry as well, yeah? And of course, hertz is basically the frequency is 1 over second, so I can write this one as well. I can say Henry over second as well, yeah? And of course, I can substitute, or you can swap this to change their places, then of course I'll get second equal to Henry over ohm as well. So of course, these are some ways where you can manipulate with the units, and of course you can get different units out of this. So we have a study tip. This one is also, I want you to be aware of. It says the inductive impedance, a resistance, let's say, that is provided by an inductance or an inductor, depends on what? Depends on the frequency of the AC alternating current, which is directly proportional, and also depends on the self-inductance, which is also directly proportional. Take a look at this one. It says inductive impedance is equal to what? We've learned that, all right, we said that it is either equals to, using Ohm's law, that is voltage over the current, whether if it is maximum with maximum, effective, or instantaneous with instantaneous. If those are not given, then we can say it depends on omega, okay, and of course the you can say the inductor as well, or the self-inductance as well. So basically, it depends on what? It depends on, or you can say it is equal to omega times L. Okay. Now, it says if a self-inductance is connected to AC source, the potential difference, okay. So when we have, remember this, says if a self-inductance is connected to an AC source, so the potential difference, the voltage basically leads the current by what? Is it leading the current like, is it 0, is it 90, is it 180, what is it, yeah? We've said that when we have a self-inductance, of course, the voltage leads the current by 90 degrees, which is going to be option B here. If a pure self-inductance, or you can say in a pure self-inductance, the potential difference leads the current by a phase angle of what? This time, instead of giving the angle in degrees, they give you the angles in, or the angle in radian, which is of course is going to be pi over 2 radian. Okay, which is 90 degrees again. Okay, now we have a sample problem here. Solving these sample problems are very important because it tells you how we can solve any questions related to this or any questions similar to this one. Let me get a sip of water. Okay. Moving forward, it says a coil of pure self L, that is what we have, which is 0.2 Henry, and a negligible resistance connected across an AC circuit or source of frequency 50 Hertz. Okay, find the self-impedance of the coil and the effective current through it, and then what else? The effective potential difference is this much. Write down the expression for the instantaneous current and the potential difference across the coil in terms of time. So let's do this one because this is a very interesting question here. Okay, so I'm not going to cover those because we will need what we have, because these are tells you what are the information that we need and what are the information that is given as well. So the first thing, remember this, we're given a pure self, or you can say the value for the inductor, yeah? So that's basically L, which is 0.2 Henry. We have a frequency, which is 50 Hertz, and we have V effective, because it tells you the effective potential difference, which is basically 125.6 volt. Okay, so what is the first thing, okay? It says find the self-impedance of the coil, correct? So this is, watch this. How do we find the self-impedance, by the way? So of course, there are two ways to do this, yeah? We'll say self-impedance equal to, let's say, since we're given V effective, we can say V effective over I effective. But let's see if we have each one of those, yeah? That is one way. If we don't have enough information to do this, of course, there is another way. We can say self-impedance, all right, or inductive impedance, let's say, equals to what? Equals to, let's say, omega times L, correct? And of course, omega equals to what? Equals to 2 pi f, yeah? And then multiplied by L. Now I can find, let's say, the self or inductive impedance. That is, so as you can see, I have frequency and I have L, so I can easily find this one. So no need to do or to find it this way here. So let's just plug in numbers here. So in this case, we can say 2 pi times the frequency. What is the frequency? That is 50, and then multiplied by 0.2, yes? Very, very good. So 2 times 50, that is 100 pi. 100 times 0.2, that is going to be 20 pi, yeah? 20 pi what? That is going to be in ohms, don't forget, because it is inductive impedance, which is measured in ohms here. Okay, now the next part here says what? And the effective current. So how do I find the effective current? If you look at this equation here, I've found this one here, and I have this one. Can I find the effective current? The answer is yes. So we'll say effective current. Let's use a different color. Okay, so we'll say effective current. Effective current here equals to what? We can say equals to the V effective over what? Over XL here, which in this case is going to be V effective that we have. It is 125.6, and then divided by 20, we can say 20 pi, yeah? And of course, you do the math, you will find the answer. Of course, it is going to be this much in amperes. Go to calculator and do the math and see what it is, okay? So in this case, let's take away this one. You can see that it is equal to 2 amperes here. Okay, so 2 amperes here. Now, moving next, what does it say? It says write down the expression for the instantaneous current and the potential difference across the coil. Now let's do this part as well. So how do we do this one, guys? Remember this. We can write the expressions in two different ways. We can either use this with a voltage leading, that is going to be V instantaneous equals to V max sine omega t plus pi over 2, that is one way, or we can say the current is going to lag, let's say sine omega t minus pi over 2. Let me write it down so that you know more of what I mean here. So for the value here, we'll say the instantaneous voltage here, that is V sub L, we can say, it is going to be V max, okay, sine omega t, all right, omega t plus pi over 2. That is one way. As for the current here, we can say current I sub L equals to I max sine omega t, or just sine omega t here. If not, we're going to take away this one here. We'll just say omega t for the voltage, but for the current, then you will have to say omega t minus pi over 2. But of course, I think this way is fair enough or good enough at this point here. But look, what I have is the V effective, not V max, as you can see here. Okay, so how do I find V effective here? So we'll say, or V max, we'll say V max equals to V max equal to the square root of 2 multiplied by what? Multiplied by V effective here, which is going to be square root of 2 multiplied by 125 point what? 0.6 volt. And of course, you can do the math or you can just leave it as it is here. That is this way. So in this case, of course, it is going to be what? It is going to be, let's just say, let's write it this way, write this one before, and then 125.6, okay, multiplied by the square root of 2, then sine, okay, omega t. But remember, what is omega here? We said omega equals to 2 pi f, correct? So for the omega, omega equals to 2 pi f, yeah? The frequency is 50, so 2 pi times 50 here, of course, that means 100 pi here. So now I'll write 100 pi and then plus, don't forget the t, by the way, 100 pi t and then plus pi over 2 here. For the, we're going to do the same thing for in terms of the current or maximum current here. We don't have maximum, so we're going to do that. We'll say, perhaps I can do it here. So we'll say I maximum equals to I effective times the square root of 2. I effective is 2 times the square root of 2, you can say, yeah? So we're just going to plug this into the equation here. Should have moved this one a little bit. Let's see if we can move this one. Oh, no, this. Okay, so let me just rewrite this one here. So we can say I maximum, which is going to be 2 square root of 2, and then sine, hopefully you can see that. That is sine just omega t, but instead of omega, we said it is equal to 100 pi and then t, and that's it, yeah? So remember, this is the equation for instantaneous voltage, instantaneous current, and these are other values that we have found, okay? So these are, or every other questions can be solved using this method, okay? So remember this is going to be for the instantaneous current, and this is for the instantaneous voltage. It makes no difference which one you write first here at this point. Okay, moving on to something different here. By the way, this question, I think it is pretty easy, pretty simple. It is just the application of the equation. Calculates the self-impedance here. So self-impedance can be found, just use the equation, yeah? Self-impedance equal to what is given here? Henry is given. So if that is the case, then that is omega L, yeah? Omega is basically equal to 2 pi f. Okay, basically these are constants of frequency times L, and that's it. You can just find the self-impedance normally. Okay, now moving on to the next question here. Says this is pretty much the same as the other one, but let me tell you one more thing about this one here. When you're given an equation like this, okay, so for example, it tells you that the source of instantaneous values of V equals to 10 sine 50 pi or pi t, yeah? So I want you to notice one thing here. What if they ever ask you to write the equation for the instantaneous current here? Because you can see here, this 50 pi t, that is basically omega t, without writing that the voltage is leading by 90 degrees. So if they ever ask you to write the instantaneous current here, in this case it becomes I max, it is going to be sine, remember, omega t minus pi over 2. Why? Because they don't tell you that the voltage is leading by 90 degree here. So, but we do know that if it is, let's say, if it is for a coil of self-inductance or pure, let's say, inductance and all that, the voltage is leading. So if the voltage, or if they don't show you leading by 90 degree here, you'll have to say the current must be lagging by 90 so that this too becomes correct. Okay, but that is not the question here. So what is the question here? It says, in a coil and all that, find the maximum value for the current through the coil and the phase difference between the potential difference and the current as well. So how do we find the maximum? By the way, take a look. Okay, so what we're given is this, for example, this is V maximum, and you do agree with me, yeah? And this is, of course, 50 pi, that is basically omega, yeah? So if we have this two here, how are we going to find the maximum current or the value for the current here? We have something here. One way to do that, because we have V maximum, we can say omega or self-impedance here equal, or inductive impedance equal to what? Equals to V maximum over I maximum, correct? So in another word, I have this one because I've given this is V maximum, yeah? But then in order to do or find maximum current here, I need to have the inductive impedance. But as you can see here, inductive impedance equals to what? So in order to find this one, this is equals to omega times L, yeah? But of course, this is omega, yeah, which is 50 pi. So we can say 50 pi multiply. What about the value for L? It is 0.1. So once you find this, you plug it into the equation, then you can find I maximum here. So I maximum, we can say then, equals to V maximum over XL, you can say here. And of course, XL equals to, let's say 5 pi in this case, or whatever the value here. Just plug in this into the equation, and then you will be able to find the answer. Okay, and of course, for the second part of the question says, what is the phase difference between the potential difference and the current? And of course, we do know that the voltage leads by, you can say 50 degrees, or you can say the current is lagging by 50, not 50, by 90 degrees, or you can say pi over 2 radian. That is also true. By the way, since this one doesn't mention that the voltage is leading by 90, that is also true if you say the current lags behind by 90 degrees or pi over 2 radian. That is also true. Okay, now these are some national exam past questions, you can say some mosaic questions. These are also very, very important, and I really hope you try to solve these questions. What is the first one? It says, an AC source with an instantaneous potential difference. So we have V maximum, you can see. By the way, guys, whenever they give you an equation, always remember, or the instantaneous, let's say, equation, there are some purpose, or there are some reason behind this. One of the reason is this is V maximum, and this is 100 pi is the omega. So of course you can use this for a lot of things, yeah? So feeds a pure self-inductance coil with a maximum current. So we have maximum current. What is the coefficient of self-induction here? So how do we do this one here? So of course, let's say we have, watch this, we have maximum current, we have maximum voltage. Using this two, or using Ohm's law, okay, we can find the self, or you can say impedance, or inductive impedance, which is equal to V max over I max. Now, using this one here, so let's say we found XL. So now XL equals to what? Equals to omega L. And of course, we have found this one. We do have omega there. So can you find the coefficient of self-induction? And of course, yes, and this is how you do that, okay? So go ahead and do that. Let's just try, see what is this one equal to. That is 25.12, and then divided by 1.6. Let's see what it is, yeah? Let's get a calculator. We have 25.12 divided by 1.6. The answer for this one is going to be 1.57. 1.57, that is going to be in ohms, yeah? Okay, now the next thing, we want the coefficient of self-induction here. You can say L equals to XL over omega, and omega is given there, which is 100 pi, yes? Okay, so we can say 1.57 divided by 100 pi, and let's see what is this equal to. 1.57 divided by 100 pi. All right, and of course the answer is going to be 0.005, okay? So which one is 0.05? Okay, that is basically going to be, okay, 10 to the power negative 3, so it is going to be 0.05, and that is, obviously I've done something wrong here. Okay, let me redo this one more time. 12 or 25.12. Because we didn't have that one here. So 25.12, okay, equals 2, or divide by 1.6. That is going to be, 15.7. This is perhaps what I've done wrong, yeah? So 15.7. Guys, always check with your calculator. Let me switch this one to, okay. So it is going to be 15.7. That is what I've done wrong here. 15.7, this is in ohms, yeah? And then, of course, now 15.7 divided by 100 pi. 15.7 divided by 100 pi. 15.7 divided by 100 pi. All right, now it is going to be 0.049. So by rounding, of course, we will get 0. All right, let's erase this one. So of course now it is 0.049. So by rounding, of course, we have 0.05. That is in Henry here. So of course now we can say the correct option is answer or part D here. Okay, so that was for this one too, right? Since I wasn't planning to do this one, but because we've done this one and of course it went wrong a bit, I'll try to do this one just to make it up for you guys. So it says a coil with an inductive impedance, right? So remember this, that is 11 ohms and a negligible resistance is connected across an AC source with a frequency of this much. Calculate the approximate value for the coefficient of self-induction of the coil here. So once again, okay, so we have XL. I believe this one is way easier than the previous one here. So XL is basically tells you it is 11 ohms, okay? And then we have the frequency is equal to 50 hertz, yeah? So find what? Find the coefficient of self-induction, you can say, yeah? Okay, the coefficient of self-induction basically. So now, what is the connection between all of these three? And of course, we do know that XL equals to omega L, very good. And of course, XL one more time equals to 2 pi F times L. We want L, yeah? So we can say L equals to XL, and of course divided by 2 pi F, which in this case is going to be 11 divided by 2 pi F, or just 2 pi times 50, yeah? That is, again, you can say 100 pi here. So we're going to say 11 divided by 100 pi, correct? 11 divided by 100 pi, which is going to be 0.035, which we can say also we can round it up to 0.04, but since we have the exact number here, so we're not going to round it up here. So of course the answer is going to be C here, because the answer is going to be 0.035 here, and of course that is going to be in Henry, of course. Okay, and this is how you can do this one too. All right, now let's talk about the third type of circuit when it comes to, let's say, Ohm's law, yeah? And of course now, a capacitor circuit. What is a capacitor circuit? Remember, when it comes to a basically we're going to connect a capacitor to an alternating source, just like what we have done with the previous two, let's say, with a pure resistance, and of course with a pure self-inductance as well. But this time we're going to do that with a capacitor only. So basically we have a circuit that is connected to a capacitor. What is alternating? Of course, or capacitor is connected to an alternating, let's say, or AC source here. A capacitor normally is a device that is, let's say, made up of two plates. You can say parallel, could be parallel plate, or well, it depends on the type of the shape of the capacitor. Let's not say parallel, because that is not the case always. And then, but what we know is this. Capacitors normally, if we just talk about this one, let's say it has two plates, and these two plates are separated by an insulator. Whatever the insulator is in between the two plates is called dielectric. So it could be air, it could be plastic, it could be any other material, as long as it is an insulator. So the insulator that is filling the gap between the two plates is called dielectric. So, but sometimes, or you can say mostly, is could be air. In a lot of cases. Okay, so what is the job of a capacitor? Normally, capacitor plates would store electrical charges here. Okay, they store what? They store electrical charges here, or you can say they store electrical energy if you want to. Okay, so a capacitor, and of course it is resembled by letter C, you can say, it is a device that stores electrical energy using two conductive plates. These plates must be conductors, separated by an insulator. Whatever the insulator that is filling between the two plates is called dielectric. It stores charges when a voltage is applied, and of course its storage capacity is measured in farads. Okay, so you can say capacitor, or the capacity of a capacitor is measured in farad. Okay, so now what do we do here? Just like all the other circuits, of course, we're going to connect a voltmeter and ammeter to the circuit. With the circuit, just like what we have done previously before. So, but Of course, we're going to have something different here, which is a little bit interesting. This time, instead of, let's say, the voltage reading maximum, the current, let's say, still staying at 0, we'll see something opposite to this will happen. We'll see that the voltmeter reading is still reading 0, while the ammeter is reading more and more and more until it reaches maximum. When the ammeter is reading maximum, the voltmeter is still showing or reading 0. Now this time the emitter is going to decrease more and more, but the voltmeter is going to increase more and more. So in another word, we can say that when the current is maximum, the voltage is 0. This time the voltage becomes maximum, but the current becomes 0 here. But remember, which one reaches maximum first? That is the emitter this time. So based on this, we can say when we connect a capacitor, let's say, to an AC source, and of course having an ammeter and a voltmeter within the circuit, let's say the ammeter reads maximum, then the voltmeter, like when the voltmeter is 0, then the voltmeter becomes maximum, then the current or the ammeter shows 0 and well. So based on this, we can say that the voltage here is not leading anymore, okay? What is leading is the current. So how can we draw this or help you understand this by drawing this? Okay, so basically we have a capacitor. Don't forget, these are the symbol of a capacitor, 2 parallel plates for now. All right, let's say, and of course this is connected to an alternating current. So let's make this one nicer. An alternating current here. Okay, and of course there is a switch. There is an ammeter which is connected to this, and of course there is a voltmeter which is connected across the capacitor to measure the voltage across this. This is to measure the current that is flowing to the capacitor here. So that is one thing that what we have, okay? So how do we tell that using representations or graphs or sine waves here? So watch this. We have one of the waves. Let's say this is for the current. Let me use a different color for that so that you can see the difference. Let's say this is the instantaneous or sine wave for the current. Of course, except on this part, we don't need this. And then watch this. Let's say these are basically maximum, or when we have maximum current across the capacitor here. So how do we represent that? Because we're saying that the voltage is lagging. So you can see here, we can say the voltage is lagging by 90. And of course, you can say this is 90 here. So, and now that is, you can see what happens here. When the voltage is 0 here, the current or the ammeter is reading maximum here. So if we move with this one here, we can say this. When this time, let's say the voltage is maximum, but the current is 0, and then one more time. So this is basically, again, maximum. This is 0 here, and then it goes on like more and more in this, yeah? So basically, this is what we have. Not a perfect graph, but of course, you see the difference between, or you notice what happens exactly right here. So at this particular point, for example, the current is 0, but the voltage is lagging by 90, you can see. At this point here, the current is maximum. By the way, this is the, let's say, V maximum. Okay, so V maximum across the capacitor, or you can say this one is 2, obviously. Okay, so when the current is maximum, the voltage is 0. When the voltage is maximum, the current is 0. Again, the max or 0 voltage, maximum current, and all that. Yeah, so of course it continues like this one. So how can we, once again, so based on this, what is the difference or what is the angle between the two? Because we're talking about lag in here, so we can say this is the voltage, or V over the capacitance here, and of course this is the current here, I over C. So the angle difference or the phase angle difference between the two is going to be negative pi over 2 radian, or you can say negative 90 degrees here. By the way, if you're going to say lagging, you don't have to say the negative, because the term lag in itself, it means that it is behind, or it is negative by pi over 2 radian or 90 degrees here. So this is, we can say, the angle between the two, or by the way, we're talking about this angle between the two, yeah? Okay, and this is what we have for a circuit, or when a capacitor is connected to an alternating circuit here. So, and we did talk about how do we write the instantaneous values for the capacitor circuit? Yeah. So of course, here's what we're going to write. Remember this. We're, once again, just like the previous one, we're going to, or we're able to write this one in 2 different ways. We can say, because the current is leading, we can start with the current first. Let's use Okay, so we can say, here is the I, let's say instantaneous value for the capacitor, we can say I maximum sine omega t. Yeah, that is one way to say, yeah? Okay, another way is, before that, let's say, what about for the instantaneous voltage? We can say V maximum sine omega t, because we said it is lagging, so we'll say pi over 2 radian, of course. That is one way. If we want to write the other way, of course, we will say, this time, we'll say I maximum, right, equals to, or let's say I instantaneous equal to I maximum sine omega t, but this time we'll say plus pi over 2, and then for the voltage here, V instantaneous equals to V max sine omega t here. Okay, so do you notice what I wrote here? We will either say the voltage is lagging by 90 degrees, or we can say the current is leading by 90 degrees here. But we cannot say, once again, we cannot say the current is leading by 90 and the voltage is lagging by 90, because that would be incorrect. You will either write this version of the equations, or you will write this one right here. You cannot write this two together or mix the two together. So either this or that one over there. So here we can say the voltage lags by 90. Here we can say the current leads by 90 degrees. Okay, now of course using Ohm's law, we have something called capacitive impedance. Yeah? So we have resistance, we have the inductive, you can say, impedance, or and of course now we have the capacitive impedance. Inductive, that would be for the inductor. Capacitive, that is going to be for the capacitance, you can say. So what is the capacitive impedance? Because of course there is a resistance to the current as well. So capacitive impedance, we can say the ratio of the maximum value of the voltage to the, let's say, across the capacitor, and of course to the maximum value of the current in the AC circuit. That is one way. Or if not, it's measured in ohms because it is a resistance. If not, you could just say it is the capacitors, or it's a measure of the capacitor's opposition or ability to oppose the alternating current as well. So based on this, for this part here, we can go with this, yeah? We can say based on Ohm's law, of course. Now we've, here's for the capacitive impedance. Okay, remember, try to remember the terms. This is inductive impedance and this is just a resistance. Using Ohm's law, of course, we're going to use this one. We'll say V maximum over maximum current. If these are not given or available, we can use V effective over I effective. If not, you can use instantaneous values. That is V now, or instantaneous values for the capacitor, and of course over the instantaneous values for the current as well. But is that the only way we can find capacitive impedance? No, there's another way that we can find this one here. But I want you to remember this. This capacitive impedance, or you can say the capacitor circuit, depends on the frequency of the alternating current as well. So if you remember in the first circuit here, pure resistance, it did not depend on the frequency. This, for the inductive impedance, let's say, or inductor circuit, let's say, or self-inductance, let's say, it did depend on the frequency and was directly proportional, yeah? Because XL was equal to omega L, yeah? And of course, omega equal to 2 pi F, which was directly proportional to this. But here, it is still, or you can say it still depends on the frequency, but you can say it is inversely proportional to this. So we can say, or another way to find this one, inductive or capacitive impedance equals to what? Equals to 1 over, don't forget, 1 over what? 1 over omega C. If not, you can say, let's erase this one. We do know that omega equals to 2 pi F, yeah? So we can say X sub C here equals to what? Equals to 1 over 2 pi F, and of course times the capacitance of a capacitor right here. So of course you can see that if I ask you what is the capacitive impedance depends on, it depends on the frequency, also depends on the capacitance of the capacitor as well. But remember, it is inversely proportional with either, or you can say each one of these two here. So inversely proportional, let's write it this way as well. It is inversely proportional with the frequency, and it is also inversely proportional with the capacitance of the capacitor as well. Okay, so remember these values, and this is how we're going to find it, yeah? That is capacitive impedance. You're going to find it this way, or you can find it this way too here. Okay, So these are basically, that's all. There's one thing I haven't actually there are two things I haven't mentioned so far, yeah? And let me take you back to this and tell you what are those here. So what exactly this one is equal to? We said that this is a resistance, so still measured in ohms, yeah? So that is measured in ohms, yeah, equals to, what about this one here? So this is basically measured 1 over, for the frequency that is measured in hertz, we can say, or you can go ahead and with this one here, and of course for the capacitance is measured in farad, don't forget. So we can say 1 over hertz, and that is also farad as well. And if we cross multiply, or you can cross multiply the whole thing, or you can say that is the ohm multiplied by the hertz, you can say multiplied by farad, all this equals to what? All this equals to 1 as well. And by the way, frequency equal to 1 over second, so I can bring the second up here, so I can say ohm equal to second over farad as well. What if I switch their places as well? If I want to know what is farad equal to, using that equation, here we can say farad, or this is the second equation here, we can say farad equals to 1 over hertz multiplied by ohm as well. And of course, these are Rosati material, by the way, okay? And of course, now, if you don't want to write this one, you can say it is equal to second over ohm as well, yeah? So these are all ways where you can, let's say, manipulate the equation, rearrange them, you can extract all these different set of units out of all this, yeah? So good luck practicing those more and more, and see if you can, or if there's anything else that you can add to the equation. The last thing I want to talk about is, how do we find, because perhaps I don't know why I haven't mentioned this one so far, yeah? And that is basically the capacitance of a capacitor equals to, that is grade 11 by the way, equal to the charge divided by the voltage across the capacitor here. Okay, so when do we use this one? Of course, whenever they ask you for the charge, let's say, that is stored on the plate, you can use this equation to find that one out. And then there is one more thing. This is measured in farad, you can say. This is measured in, that is charged in coulomb, and this is measured in voltage as well. So once again, you can manipulate this, and of course, you can rearrange this one to get different set of units out of this one as well. Okay, now the last question, okay, and then perhaps the last two things for today says, what does the capacitive impedance depend on? We said that it depends on two things, two variables. The frequency, which is inversely proportional, and also the capacitance of the capacitor. Again, it is inversely proportional. So we have a study tip. It says whenever capacitance is given, you can always find the capacitive impedance. You can always find XC, and then because you are going to need it, no doubt. And then the last thing for this session says, how does the impedance of a capacitor in an AC circuit vary when the frequency varies? Because we said it is inversely proportional, yeah? So when the frequency increases, the capacitive impedance decreases, and vice versa. So we'll say it varies inversely with the frequency. Next time, inshallah, or in the next session, we're going to solve some of these questions, and then later on, we will add all what we have studied, the pure resistance, inductance, and of course the capacitor, all combined in one circuit.